From ContainerDays Hamburg, this video is proudly presented by Dux IT.
Well, thank you very much for joining this session. I don't know what you're expecting. I hope something interesting comes out of this talk, because this started as a very, very experimental project within my company, small startup. I'll talk about it right now, and turned out to be, hopefully, a thing that might be interesting for others. I'll illustrate how we use this for a particular use case, but I think can apply to many other use cases. So bear with me. First of all, I'll start with a little bit of description about me. This is the formal slide. My way of basically talking about me is that I try to do crazy stuff, sometimes even stupid stuff, researching on trying to come up with new ideas, new technologies. And most of those stupid ideas are stupid, some maybe not that much. And I want to present today one of those. Let's see how it goes. TLDR, or if you want to take something away of this, I've given quite a few talks, especially in the Postgres ecosystem, which is my world. I work for a company called Ongres, which means on Postgres. Guess what we do? You'll see a few things about Postgres today, probably, even though I'm focusing on container registries. But there's my website, aht.es. There I have more than 140, 150 talks, most of them with slides and videos. If you want to check out some content about Postgres, Kubernetes, and Java, a few other things. So let's talk about containers, right? And let's talk about container images in particular. And one of the realizations that we can make is that if you look at how container images are built, there are typically a lot of variations, customizations, derivations, call it however you want, right? There's no like the Postgres image or the WordPress image. There are multiple, right? So let's talk about this. First of all, I don't need to explain you, probably you all know that container images are immutable. And this is great. This is one of the paradigms that enables running containers, right? I'm not going to spend a lot of time here. However, on the other hand, being immutable means that I cannot change them, obviously. That means that if I need some piece of software that is not part of this image, it's not built in with this particular binary or program or file or whatever, I need to create another image. One of the best ways of doing this is by derivation or augmentation. For example, I can take a Postgres image. If I'm using Docker files, for example, I can just say from Postgres, right? And this is an easy path. I just add my binaries and I'm done. Well, the reality is that it looks like more like the picture you can see on your right? This seems to be easy at first, but ends up being complicated. First of all, because now you become a maintainer. If you're just consuming an image, you're a user of that image. You're probably not responsible for security upgrades of that image. You're probably not responsible for the architectures, for building it, for all the life cycle of building container images. But from the moment you do a from something, now you are the maintainer. And you now bear all these responsibilities. Second, because building images, if you're, for example, compiling software, that's going to imply bringing compiler tools that you don't want to be present on the final image. You're going to create multi-stage images, and it starts being more complicated, right? And then depending on what you're adding to the image, it can become a complex process. That's okay. At least we have the possibility. But it's not for free. So it is easy at first, but can get complicated. So this is one of the ways that we're augmenting images. Now let's look at the landscape. Let's look at the reality, how people are building images. For example, if we look at Rocky Linux 9, there is users confused about all the different varieties. So there is varieties. This is this is a pointer. So there's a base image, which contains a starting base for building the container images with Rocky Linux. But then there's also a minimal one, which is like tiny one, doesn't even have a package manager, right? So that is the tiniest one that we can have. Then we have UBI, which is another set of images from Red Hat that you can use based on a slightly different concept, a reduced set of packages, but also very minimal. Then there's Toolbox. So you can see that there is a lot of varieties here. If we look at my Postgres images, not mine, I don't produce these images, but the official Postgres images on Docker Hub, for example, we can see that the tag starts looking like a cloud tag more than anything else. There's obviously tags for different versions, but there's also tags for distributions based on Debian Bookworm, on Debian Trixie, on Alpine, because different users want different base packages. And this creates a whole set of explosion of versions, because now I want this particular version on Bookworm, this particular version on Trixie, this particular version on Alpine, this particular version with, I don't know, debug symbols, right? And they're starting a kind of combinatorial explosion of different tags and versions. Obviously, not all of them are produced, because it would be probably not feasible. Same with WordPress. I was just taking some examples. You can see that it's a mess in the good sense, right? There's variety, there's options, not criticizing, but it becomes complicated to understand, to manage this. So much that even, for example, the .NET container images need to explain what is the tagging scheme. Oh, it follows this pattern, right? Because there's so many possible combinations of images, right? There's a target application, there's the environment, there's where it's based on distro.ls, whether then it's a Ubuntu chiseled image, you get the point, right? It becomes, again, complicated because it's essentially combinatorial explosion that is great for providing variety, but on the other hand, it's not even fully exploded because it would mean creating too many images. So there's obviously a need for creating a lot of image, let's say, variants. Now, let me tell you a little story about my particular use case, Postgres. Probably you'll know about Postgres, right? But just in case you're not familiar, let me talk briefly about Postgres extensions. Postgres extensions are a mechanism to augment the functionality of the database, Postgres database. You can add an extension can add a new data type, a new function, or can completely change the Postgres query planner and do something different. There's extensions for time series data, for sharding Postgres and transforming it into scale-out databases, for GIS, for vector, for you name it, right? There's a lot of extensions. You can think of extensions like browser plugins, right? So small pieces of code that you can inject into the database and get additional functionality. Extensions are something that most Postgres users love. There's barely no Postgres installation without extensions. Almost everybody uses at least one or a few extensions. And it's quite normal that people use several extensions. There's also quite a long tail of extensions. It's not that most people use 2 or 3 and that's it. No, there is a lot of extensions used, even though not everybody uses the same ones. And there are a few that almost everybody uses also, but there's a really long tail of extensions used, right? In total, most people are happy if they can have a catalog of something between 200 and 400 extensions, but in total, there's around 1,000, 1,100 extensions available in general. And importantly, these extensions are typically produced by third parties. They're not produced by the Postgres project. So where the place for typically finding extensions is just a GitHub repository. Right? So it's a random, let's say, repository on the internet where you can find a Postgres extension. It's very easy to create, let's say relatively easy to create Postgres extensions, right? So that's why they grow in number very easily. So now the question, let's say you want to produce a Postgres image, container image, with extensions so that users can use them. What do you do based on these requirements? Let's look at several options. The first one is what I call the fatty container, right? Easy, okay, let's pack them all. That's it, end of story. You'll probably get a 4 gigabyte container, more or less. I mean, it's not that big. Well, actually, a Postgres container can be down to 40 megabytes. They're trading 2 orders of magnitude if you do this. But now think about the security implications. All those extensions are random pieces of code created by anyone on the internet. Not all of them are safe. Not all of them are free from security issues. Do we want to pack a lot of security issues into your container image, most of which you probably will not use, or any given user at a given time will probably not use? I'm not sure about that. But also because of the size of the image, size matters. At least in this particular field, size matters. If I need to restart a container and it needs to download the image, a new version, for example, this is going to cause downtime on my database. And I don't want Postgres to be down for 30 seconds just because it's downloading 4 gigabytes or more, 4 gigabytes of an image. So I don't like this approach very much. So much that almost nobody follows this approach. Makes sense. There's option number 2, which was the subject of a talk I gave at KubeCon a few years ago. Here's the link if you want to check it out. And it's basically what we're doing on an open source software that we created at my company called StackRes. And it's basically injecting dynamically the extensions into the container runtime, obviously not the container image, which is immutable. So basically, we start with a container with no extensions on it. It's running. And then dynamically, at any point, via CRD or several other mechanisms we have in Stagres, you can say, I want to have this extension. And then there's what we call a local pod controller that runs as a sidecar to the Postgres container runtime and connects to a repository, download the extension, verifying the digital signature, and deploy to Postgres primary and all the replicas across the cluster so that it's available everywhere. This works. It's a little bit involved. If you're restarting nodes, if you're upgrading nodes, there's kind of a logic there to keep the cluster synchronized, that all instances of the cluster have the same extensions, but it works very well, and in real time, you get the extension. However, it's also not perfect. There is a little bit of a startup time overhead, because sometimes if you start afresh, you will need to re-download all the extensions before starting Postgres. And also, it's not perfect from a security perspective. Technically, we're actually a little bit violating the idea of immutable containers. And some security analysis tools will flag this. So we started researching for another option. But let's look at the core of the problem with extensions. So there's option number 3, which is what you would typically do with, let's say, a regular or what I call static container registry. Just let's generate all the images. Right? Maybe we can do this. I don't know how good you're in maths, in particular statistics. I'm not very good, so this formula may be wrong, but this is what I came up with. Please correct me if I'm wrong. But this is my understanding of what is the number of images I need to generate based on the amount of extensions that a given user may pick at a time, called R, and the total number of extensions available in the catalog, called N. How do we estimate this number? Well, let's look at a term that is the one in the middle of this sum, right? This is the term you can see here on your right side. And let's substitute by several numbers of n to get an estimate of the size of this. So for 10 extensions on my catalog, I need to produce 252 images. That's maybe doable. But if I want to support 200 images, I need more number of container images produced than the number of atoms in the universe. And I'm not going to pay for this cloud bill. Right? So, this option doesn't look like really feasible. Fortunately, we've shown option number 1, number 2, number 3. There's going to be a number 4, right? Yes, there is a number 4. And that number 4 is to dynamically generate container images, which is the subject of the topic today. So, welcome to Dozer, the Dynamic OCI Registry. First step, we need to do like a prerequisite. And it's, let's build Postgres extensions and pack them as OCI images. This is something that I believe has value on itself so much that I wrote a blog post about it. You can see here. And it's basically saying OCI is an excellent distribution format for any kind of software. And Postgres extensions, whether you're running on containers or not, you should pack them as OCI images. For us, it's going to be a prerequisite. So let's assume now we have compiled all the Postgres extensions, is 200, 400, whatever it is, right? And deploy them as OCI images, or we have them available as OCI images. Now what do we do? Well, we can use this software called Dozer, Dynamic OCI Registry. It's basically an implementation of the OCI distribution spec from scratch, right? With the main goal of composing images on the fly. And this is the key. I'll explain now basically how it works, but it's technically possible, even though at first place it didn't seem that it could be done. But yes, it can be done, and it works, right? So it is a registry that composes images on the fly. By the way, this is not doing Docker build behind the scenes. That would be very slow. And by very slow, even if it's a few seconds, we're talking here real-time image generation, milliseconds. Right? You do a Docker pull to the dynamic registry, and you get an image. That's it. The image, once pulled, is indistinguishable from a, let's say, statically generated image. It's just an image. Right? The magic happens on the registry. So what it does is that it takes pre-existing layers and composes them into a new image based on your preferences. I'll also explain now how you express your preferences for the image. The dynamic generation logic is custom. I don't know what you're going to do with this. I know what I'm doing with this, which is serving Postgres extensions, but maybe you want to do something else. Maybe you want to serve different data sets with an AI image, for AI, right? And you want to use different data sets. You want to compose different data sets. You want to do something else, right? So the business logic is custom, and as such, it is implemented as an interface. There is an interface on the software, and you implement it, and you get your business logic, right? There's a similar project to this that I realized midway, actually, during the development of this, despite all the research trying to find someone who has done such a stupid idea as I did, and only found another crazy guy that built Nix3. I don't know if you've seen it, but it's basically the same concept applied to Nix packages. So you can generate dynamically OCI images based on Nix packages, and you can get more tools as part of those packages. So how does it work? Well, this is a drawing of how a container image looks like. I guess you're all very familiar with this. It's basically a set of layers, and then one or more index or manifests that represent the content of that image, the metadata of the image. Even though this is a more general diagram, the most important ones are the image manifest itself, which is in reality the image, and the runtime configuration. So if we want to generate a dynamic image, assuming that we already have a set of layers pre-existing, the only thing that we need to modify or generate dynamically are these areas highlighted in red. And this is obviously for a full-fledged multi-architecture image with its index and all that. For single architecture images, it's obviously simpler because I just need to modify a couple of those. So let's look first at the runtime config. The runtime config is the manifest that container runtimes need to run the container image themselves. This runtime config is for the most part static, meaning I don't need to change it, or yes, right? But there's a section called rootfs history, rootfs type, rootfs diffs IDs, right? That contains the digests of the uncompressed, this is very important, layers that form part of the image. This is used to build the file system, right? The effective file system on which the container image is going to run. So it's required like this. If we're adding layers dynamically, we obviously need to have an appropriate runtime config containing those entries there. So this is an area where we need to generate dynamically. The rest of the runtime config is something that we can modify or not. We can decide what we want to do with it. And the business logic of Dozer allows you to use whatever you want. But Dozer is able to plug in and generate and build in dynamically the diff IDs of those layers you're using as part of the runtime config automatically for you. The other part that we need to modify or to generate dynamically is the manifest, the image manifest per se, which first of all needs to identify which part the runtime config that we just dynamically generated first place, and then add all the layers that belong to this image. And conceptually, this is it. Obviously, then we can talk about the additional indexes for multiple architectures and all that. But with this, you can generate a dynamic image. You can do this even manually. That's what we did when we were prototyping this. And it just works. Because a dynamic image, assuming again that you have the layers already built, is no more than creating manifests dynamically. Obviously, the implementation is much more complex than this, and there's more things to do in reality, but the concept boils down to this. Now let's talk a little bit about how to express the user preference. According to the OCI distribution spec, this is how it looks like what we typically write at the end of a Docker pull command. I call this the URL to make it simple, but technically it's called the name and the reference of the image. Well, they need to follow some regex patterns that are part of the OCI spec. And this is how we specify. So how do I really say, okay, let's say I want a dynamic image. Let's say I want Postgres with a few extensions. How do I encode this into here? And the reality is that, well, first of all, in Dozer, we don't prescribe anything. You can do anything you want, right? It's up to your business logic to decide how do you want to run this dynamically. But if you think about it, you need some way of encoding this selection of components as part of this name and reference. And they're a little bit limited because of this specification that limits, again, it's characters allowed and the number of characters actually that can be had there. So for our particular use case, which is not prescribed in Dozer, so I'm going to use it just as an example, we have come up with a scheme that we call the URL. After all, when you do a Docker pull, there's a URL there. And by using paths, we can keep with this analogy and keep this look like an URL. So for example, we can say, okay, this is the name of the base image, right? And then I'm going to use a separator, /e, to signal that there's extensions coming afterwards. And then all the extensions separated by a /. This seems very straightforward and actually feels natural for users. In reality, we have a more complex scheme in our particular use case, because we're using this to serve Postgres images. That's not part of this talk. We use a /e for extension. There's like a /a for add-ons and a few others there. The reference is unfortunately ignored. It's tempting to use it, but how do I don't have, reference is usually the tag, right? So it's a version. But in reality here I have potentially multiple versions. I have the Postgres version, I have the extension 1 version, I have the extension 2 version. So how do I encode this into the reference field? We did a little bit of research there, but it's very limited in length. So in reality, there's not much you can do that is also human friendly with the reference. So we decided to basically ignore that and instead encode the versions explicitly into this URL with a /. So now we can version every component independently. Again, this is our example of how we implemented the custom business logic of top of Dozer. Dozer is a generic container registry that does not prescribe any way of using it, right? Now, there's also potential limits with the URL length. Docker limits it to, I think it was 2,000 characters. But anyway, there's also ways around this, right? So, anyone wants to see a demo here? Not everybody. Let's skip it. Or unless you're going to raise more hands. I may change my... All right, now, thank you. Of course, this is going to be a live demo, which means it's going to fail. So I have a backup, which probably will fail also. You can throw tomatoes. No, please. Anyway, so this font size, I guess it's OK, right? Let me SSH somewhere else so we can... Actually, I think it's pretty big, isn't it? Is it OK? All right. So let me... So I just needed an SSH to a cloud instance, so I'm not relying on Wi-Fi other than for SSH. And this is an empty server Ubuntu machine. I just installed Docker, okay? So let's do a Docker pull to a test .ci server. And let's pull a Postgres image. Nothing special here. It should work. Will take a few seconds, right? This is going already against Dozer plus our custom implementation, right? And this will download a Postgres image. Nothing special here, and downloaded the image. And here we have it. Now let's say I also want to get a specific version. For example, this one, 16.3. As you can see now, this is already something different. Well, actually, we could create a container image on a regular registry that will like this. But in this case, there's more magic happening behind the scenes. Here we have our custom logic that is receiving this URL. It's parsing this URL. And is determining that we are asking for a specific version of a given image. So it's doing a lookup behind the scenes, creating the layers, and serving the image. OK. So far, so good. Let's actually run this. So let's do a Docker run. Let's give this a name. Let's pass the Postgres environment variable that we need to run this. And this last image. Right, this should get us up and running soon. And let's just connect to this. Let's use Postgres. Let's connect as the Postgres user, which is the one that exists on the image. And let's run a query on Postgres. Well, first of all, let's see that Postgres exists. And unsurprisingly, it's Postgres 16.3, right? Good. And now let's run a query to list the extensions available on this container image. There's a function. that will list us the extensions available on this container image. Well, it should be 0. These images are still a little bit experimental, but as of now, we have a few extensions that come by default. We will remove them. But let's see that there's only these 6 extensions. So now, let's try to do a Docker pull and add some extensions here. Right? So I type /e, and then I need some extensions. So can anyone help me? For you to see that this is not fake, please say something. Rum, thank you. This I heard. Let's try it. Not all are available for this particular version, but let's see if it works. Looks like yes. So it's interesting. Well, first of all, we apparently got this RAM extension here. The second thing to note is that all layers existed, right? Except the last one, which kind of makes sense. If it generated an image with all components that we already had downloaded and then added something on top, then it makes sense that it pulls just this layer, right? All right, let's add a few others. I'm running a little bit out of time, so I'm just going to go a little bit faster. Let's say L3, let's say Citus, and I don't know, another one. Mime, oh, I don't even know this extension, what it is. Good, so it also works, and you see that it pulls 3 layers, right? That's good. And now let's delete the previous. Yeah, absolutely. It will consider a new one. Well, actually, there's RAM twice. That's an interesting use case. But I guess you want to do something like this, right? It re-downloads all those layers, which also makes sense, right? Now, let's delete this one and do a Docker run. But in this case, instead of running this image, I'm going to run. Actually, by the way, this is interesting. Here we have the images. It looks a bit weird, but this is how I can have these dynamic images, right? And now I can do a Docker run, and I'll pass this image. And now if I say select all the extensions, I can see now here that all the extensions that I requested are present in my image. Cool, it worked. Lucky me. All right, so what is Dozer today, and what are the next steps? This is a software written in Java. Don't scream yet, modern Java. You may still scream a bit, but bear with me. I love it. It's a great language. And Quarkus, also great. As I said, the dynamic generation is a custom logic that you can bring in. It's just implement essentially an interface, which basically says, given this name and reference, what I call the URL, tell me the array of layers that I need to bring in, the digests. And Dozer builds everything for you. That's all that you need to do. It supports software today, multi-architecture, S3 backend, token authentications, multi-tenant, quite a few other things. Interesting part is that mapping this URL to layers is usually something that is not easy to do just looking at the URL. Sometimes, or essentially for our case, we definitely need metadata to get from the images. So Dozer has also implemented a mechanism for automated metadata collection. It's optional, you can run it or not. And it basically does is when a component image, it's uploaded, is pushed to the registry, it generates metadata from this image and puts it into a database, unsurprisingly a Postgres database. If you want to put it somewhere else, you can write an implementation of a given interface, and gives you a lot of metadata that you can later query on. Again, this is querying that is part of your business logic. So Dozer just puts it on a Postgres database and gives it for you, right? But it's very useful. This is, for example, what it looks like in our particular use case, where we have some fixed fields, which are part of the usual OCI spec. And then under the field custom labels is where it essentially stores all your labels from the container image that you created, the base image. And so what is going to happen tomorrow? It's going to be published as open source software under AGPL version 3 license. It's months or weeks away from this from happening. After that, we aim for full OCI distribution compliance. It's not there yet, but not far. And from here, there's a lot of discussion. We would like to talk with the community to see if the name and reference part of the spec can be somehow augmented, because they're a little bit limiting for these particular use cases as of now. And of course, potentially support bindings for other non-Java languages. And that's it. The slides are on this QR code if you want to check them out. And I hope we have some time for questions. Thank you. Yeah, so the server is not empty because all the component images, what I call the building blocks, are or have to already be present on the server. So it's not that the server is going to pull the images from somewhere else. They need to be pushed to the server already, the building blocks. I hope that answered the question.
How is caching handled if reference is ignored?
Yeah, so if basically the image manifest always returns a digest, and this digest is what is used for caching purposes. And the digest is a fixed one if the components, if the resolution of the URL to components doesn't change. But of course, because it's dynamic, it could change, right? So essentially, if you wanna use an image as is, what you need to do is to pin it. And to pin it means get the digest for the image and then use that as a reference. So actually, the description I mentioned is not exactly complete because it also supports the classical mechanism of saying, give me this particular image at this particular digest. That's where you specify the reference, and so essentially you can pin any version. And it's actually the recommended way to do so. So once you generate a dynamic image, you get the digest, and you pin it, and then you pull the image by digest so that you always get the same image, a fixed one.
Thanks. There's another interesting one. How do you create compatibility metrics with extensions and Postgres conversions?
Well, that is a little bit out of the scope of Dozer, first of all, but okay, answering this from my perspective of Postgres, and from our perspective, it's also not our real problem as of today. This is an interesting subject, but for now, we just want to provide users with whatever they want. Now, if you ask for a set of 2 extensions that do not work well together, well, sorry. There is actually a nice study. There's a paper published about some researchers that did basically a test of every pair of extensions together, whether they work or not, and they found that approximately 10 or 20% of pairs of extensions do not work together. So this is definitely a problem, but it's not that we are trying to solve as of today.
Now I lost track. Which was? Let's go with the house upvoted. How are the images extensions described to work with the Dynamic OCI Registry?
Are the images extensions described?
The top one.
Yeah. I'm not sure exactly what it means. What I would say is basically, so here we take Postgres. We build the Postgres image. It just has Postgres. Then we build the extension Citus. It just has Citus. Then we build the extension L-tree. It just has L-tree. Then we build the extension Vector. It just has Vector. These are all OCI images on themselves. These images get pushed to Dozer as a regular registry, Docker push, right? We don't use Docker push, but you get the point. And then you can request a dynamic image. And it does all the magic behind the scenes, right? Of course, we implemented this custom logic, which actually goes talk to the database, basically say, oh, you're asking for L-tree and you're asking for Postgres 16.3. Is there an L-tree implementation that is compatible with Postgres 16.3, this particular architecture and some other checks that it does? Yes, then it finds the digest and composes the dynamic image.
Thank you. The top one, instead of building in a full new registry, could that be a proxy to the existing one like Harbor?
That is a good question. So we consider several things. One of them was actually using an existing registry and just augmenting it. But most registries are written in Go, and our team was proficient in Java, not in Go. So there was a language mismatch there. Building it as a proxy, it's an option that was considered also. But in reality, what we saw is that our Dozer itself has some specific requisites in terms of image storage, fetching metadata, for example. What's one of the key things that we needed some custom implementation. And it made it more difficult. Also, we want simplicity in deployment. And this adds kind of little bit of friction, more moving components, more moving parts to it. So we decided to go full route of building the registry completely. In reality, registry is just a CAS, it's just a container addressable storage. It's not a big deal. The API, the HTTP API, it's relatively short number of methods that are exposed, and it was not a big deal. It was much more complicated to implement some parts of the dynamic part than the image or the registry per se part itself.
Perfect, thanks. The next one would be, what if I need images to be signed to be run in the cluster? How to do security? All source OCIs, which can be selected, need analysis.
That is a great question. So this is something that's not going to be present on 1.0, but definitely is going to be present on one of the later versions. We're doing this in part because of security concerns also. So this also has been part of our thoughts. So signing the images that are composed dynamically is still possible. We just need to sign them dynamically also, right? There's no other way, but it can be done. Of course, the signing artifacts need to be somehow delegated to the dynamic generation of the image, to the business logic, right? Which is not maybe perfect, but it's still doable. But on top of this actually enables a more fine-grained security because we can do independent analysis on all the components. So what I'm saying is, like, let's look at security analysis. We can do security analysis of each building block first place. And then when we compose dynamically, we know that we are adding vulnerabilities or not, because we can have security analysis for all of those. Actually, I can extend this question to something like SBOM. We're also planning of dynamically generating dynamic SBOMs, composing all the elements of all the composed layers themselves. Because if those layers have the appropriate SBOM, we can merge them and generate a total SBOM that contains all the components of the dynamic image. So there is still work to do. And of course, once this is open source, anyone will be more than welcome to join and contribute, but it's something which is definitely on our roadmap.
Are you up for more questions?
Okay.
How you handle file conflicts when layering the copy and write layers?
Yeah, another great question. Thank you so much. Well, there's an assumption built into everything that I mentioned, is that there's no overlapping. That's it. In the case, for example, of Postgres extensions, there is no such overlapping. They're all distinctly separated. And if you want to do some things with layers that will overlap, well, I mean, good luck. I wouldn't do that. It will probably, I mean, Dozer will compose the layers regardless. There's no check for that. There could be a check for that. There's no check as of now. It's up to you to decide whether that works or not.
Thanks for that. There's another one around, can you dynamically aggregate multiple plugins in one layer if they're commonly used together?
Yes, of course. And actually there's also some limits in the number of layers that normally container runtimes can accept. Typically this limit is 128, also quite limiting if we're talking about composing multiple layers. So at some point we may want to do that also. And if you, so right now you cannot request more than 128 extensions at a time, which from the Postgres use case is not a problem. I don't know anyone using more than 128 extensions at the same time, but could affect other use cases. And for this, well, the only option is to aggregate partially some layers. Actually, Nixery, the other repository that does dynamic generation of OCI images, actually is able to do this, because sometimes if you're asking for packages, a given user may ask for a lot of packages. So there's a technique implemented there to look at sizing and determine like the smallest ones to bundle them together. From our implementation that is built on top of Dozer is specific for the Postgres use case, we don't want to do this. Extensions are self-contained, are atomic units of code, plus their dependencies, and they are good as that, but all the implementations can do differently. This is determined at image building time, right? So you can do whatever you want also. And then there could be logic also to aggregate them directly, but it's not done as of today.
Thanks. I would assume, how do you create plugin images is described in the documentation, right?
These plugin images, if we're talking about Postgres plugins, this is something that we're building ourselves, and you can do with Docker build, whatever you want. So it's up to you. They're building blocks. They're regular OCI images. You can build them however you please.
Okay, then let's wrap it up. And thanks again for the amazing talk.
Thank you.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.